Hey there, AP Pre-Calc. This is Miss Adams from Flamingo Math. We're looking at lesson 3-7 today. This is day 1. We're going to put together all the concepts from the last few lessons that we've seen, and we're going to write equations using sine or cosine functions, given some verbal description of periodic behavior. Then we can use the equation as a mathematical model and make predictions and interpretations related to real world phenomena. You're going to need a calculator for this lesson. In example 1, we have a figure that shows the depth of water along a seawall. If the depth is 5 feet at low tide and 11 feet at high tide on a given day, low tide occurs at 6 a.m. and high tide occurs at noon. Let's label our graph to represent that. So low tide occurs at 6 a.m. Low tide is 5 feet. High tide is at noon. That would be at 11 feet. So 6 p.m. would also be low tide. And then at midnight, we would also have high tide. Let's call this second 6 p.m. as 1800 hours. 18 is the same as military time for 6 p.m. So if D represents the depth of the water T hours after midnight, we want to use a cosine function in this standard form here to model the depth of the water. We can write that as D of T. The A value is our stretch or amplitude, so the A value is 3. And cosine, we would switch pi over 6t, I believe. And our midline is at 8. Let's verify that. If 2 pi over b is the period and the period is 12, then b must be pi over 6. And we knew the a value was 3. Use our model to find the intervals of time when the tide is rising. It appears that the tide rises from 6 a.m. to noon, from 6 a.m. to noon, and then again from 6 p.m. to midnight. Moving on to example 2, we have the height above the ground of a yo-yo can be modeled by this equation h of t, where h represents the height of the yo-yo in feet above the ground and t represents the time in seconds since the yo-yo was first dropped from its maximum height. When does the yo-yo return to the maximum height for the first time? So I'm thinking about the graph. Let's make a sketch of the graph here to the right. If we know 2 pi over b represents the period and b is pi, then 2 pi over pi is going to be a period of 2. So 2 seconds is the first time. We want to find the maximum and the minimum heights that are reached above the ground by the yo-yo. So t, 2 1/4 plus 1 1/2. I'm taking this d for 2 1/4. We know d is 2 1/4. And we're going to use that to answer part B. We have 2 1/4 plus the a value of 1 1/2. That gives us 3.75 feet for the maximum. And if we subtract, we would have 2 1/4 minus 1 1/2. So maximum here, 2 1/4 minus 1 1/2 gives us 3/4 of a foot as a minimum value. And we could label that here on our graph 2 and 3.75 is our max, and 1 3/4 of a foot would be your minimum. Moving on to the next example, this is talking about simple harmonic motion. An object that moves on a coordinate axis is in simple harmonic motion if its distance from the origin at some time t can be given either by this function a cosine omega t or a sine omega t. The motion has amplitude. The maximum displacement of the object from its resting position, and the period is 2 pi over omega, where omega is positive, and the period gives the time it takes for the motion to go through one complete cycle, and the motion has a frequency if we calculate omega divided by 2 pi, which is the number of oscillations per unit of time. Now we want to use cosine if you are pulling an object down, and we want to use sine if an object starts its motion from rest. So you got to consider those equations. Example 3 has us given a point on the tip of a tuning fork, vibrates in harmonic motion described by this equation, where omega for the tuning fork has a frequency of 386 vibrations per second. We want to answer in radians. We're looking for omega. They gave us the frequency in our definition above as omega over 2 pi, and here they're telling us the frequency is 386 vibrations per second. So our omega, if we solve for omega, omega is 772 pi radians per second. And I'm happy with leaving my answer in exact instead of decimal. In example 4, we're looking at a ball on a spring is pulled 6 inches below its resting position. So here's the first instant we have to consider which equation are we going to use if we're pulling something down. The period for the motion is 4 seconds, and our job is to write the equation for the ball's simple harmonic motion. So let's make a note of that. If we want to pull an object down, we're going to use the cosine function because the ball is pulled from the rest, pulled down from rest. Or the origin, if you want to think about the origin being the resting spot. So our start is at, we know 2 pi over omega is 4 seconds. So omega is pi over 2. And our A value has to be the absolute value of -6 to pull it down. So our equation that we would want to use would be D equals A cosine omega times time. So D is -6 cosine pi over 2 times T. Okay, example 5. We have a mass oscillating up and down on the bottom of a spring, assuming perfect elasticity and no friction or air resistance, and it can be modeled as harmonic motion. If the weight is displaced a maximum of 4 centimeters, find the modeling equation if it takes 3 seconds to complete one cycle. Assume the object starts at rest. If the object starts at rest, let's make a few notes here. Assume the spring is at the origin when t is 0. We'd use the sine model. We know A is 4. We know the period is 3 seconds. So our model, let's think about this. 2 pi over omega is 3. So omega is 2 pi over 3. And then finally, we could say our model would be, using the sine model, d equals a sine omega times time. Our model would be d equals 4 sine times 2 pi over 3t. So that wasn't bad. Moving on to example 6, let's see what we have here. Oh, this is an interesting one. A Ferris wheel is constructed such that a person gets onto the ride at its lowest point, 5 feet above the ground, and the ride reaches its highest point at 125 feet. The amount of time it takes to complete one full rotation is equal to 8 minutes, and the vertical position of the rider can be modeled as a function of time t in minutes, since boarding by the equation of the sine times b t minus c quantity plus d. We want to sketch the graph of the rider's height with respect to time for one cycle. So I want to know where the midline is. If we're 125 at a max and 5 at a min, and we want half of that, which is 60, and 60 is going to be our A value. And we start at 5 feet above the ground, so our midline is 65. So we want to sketch that in here and call that our midline, y equals 65, because they said we started at 5 feet above the ground, and if our A value is 60, that's going to have to be our location. So our first point would be at 0, 5, and we go how many minutes? 8 minutes later, we would have to be back at 8, 5 for starting at 0, 5. And then in the middle at 4, we would have to be 125 feet above. And then we need halfway between 0 and 4 would be at 2. So at 2, we would be at 65 feet. And then halfway between 4 and 8 would be 6. So at 6, we would be at 65 feet, and we have the rotation of the Ferris wheel looking like a sinusoidal curve. So what did we discover from sketching that? We know A is 60. We know B is 2 pi over 8. 2 pi over B is 8. B is pi over 4. We know C is 0 since we started at time 0, and we know D is 65, so we can put together the equation for part C that is not showing up on my screen here. So the equation is negative 60 cosine pi over 4 t plus 65. So we know the equation for part C. And then for part D, at what time is the rider at 65 feet above the ground? And we already calculated that at time t equals 2 and at time t equals 6 minutes. The rider is at 65 feet above the ground. That's the end of day 1 for this lesson. Join me tomorrow for the conclusion.